Welcome everyone. Welcome to the lecture series on VLSI and microelectronics subject. It is a subject in 7th semester BTech ECE. The course code is EC702. I am Paulu Sridhar, Assistant Professor, Department of ECE, Guru Nanak Institute of Technology. So, in this slide, we will see which course outcome is fulfilled in this lecture. Our lecture is lecture number 10 of the lecture series on VLSI and microelectronics subject. So, our lecture series will consist of 45 number of lectures and the credit is 4 of this subject, and the total contact hours are 3 lectures plus 1 tutorial per week. That's why it is 4. The credit is 4. Next, we are in module 3, that is analog VLSI design, circuit design. So, here now we will see which topics we are going to study in module 3. Small signal model of the MOSFET, analog sub-circuits like the MOS switch, active resistors, MOS diode, current source and current sink, current mirror, current and voltage references, voltage divider, MOS equivalent of PN junction voltage reference, threshold voltage reference, band gap reference, switch capacitor, resistance, emulation of series, parallel and series parallel circuit, switch capacitor integrator and filter, CMOS differential amplifier and design parameters, output amplifier and the two-stage CMOS op-amp design. Now we will see the course objectives and also which particular course objective is fulfilled in this lecture number 10 of this lecture series of VLSI and microelectronics subject. So let us see the course outcomes. So the first course outcome is able to describe scale of the integration SSI, MSI, LSI, VLSI, Moore's law, scaling, short channel effect, VLSI design flow and architecture, and contact gate level circuit with PAL and PLA concept. The second course outcome is able to analyze CMOS inverter voltage transfer characteristics with the parameters VIL, VIH, VOL, VOH, VTH, and based on the knowledge of digital circuit design methodologies like CMOS pass transistors, TG, DCVSL, dynamic logic, NORA logic, able to construct schematic of the combinational sequential circuit SRAM DRAM cell using the MOSFET. Now, the third course outcome is based on the fundamental concept of the MOSFET characteristics and model, able to calculate value of the resistance of the current source, MOS diode, current of the current mirror circuit, voltage of references such as the voltage divider, threshold voltage and band gap, emulate resistance of the switch capacitor circuit, gain of the switch capacitor integrator and first order switch capacitor filter. The fourth number course objective is with the help of the MOS transistor model able to calculate the value of the parameters to design CMOS differential amplifier and two-stage op-amp. The fifth number course objective is able to define or describe fabrication steps of the IC, that is the integrated circuits, and construct the stick diagram and layout of the CMOS inverter and basic gates based on the lambda and the micron design rules. The sixth number course objective is able to calculate gate delay, dynamic power, short circuit power and leakage power and total power consumption across the CMOS inverter circuit based on the derived expression of delay and power. So these were the 6 course objectives that will be fulfilled after the completion of the course VLSI and microelectronics. Now let us see which course objective will be fulfilled after the completion of this lecture number 10. So let us see, based on the fundamental concept of the MOSFET characteristics and model, able to calculate value of the resistance of the current source MOS diode, current of the current mirror circuit, voltage of references, voltage divider, threshold voltage and band gap, emulate resistance of the switch capacitor circuit, gain of switch capacitor integrator and first order switch capacitor filter. So this course objective, that is third number course objective, is fulfilled after the completion of this lecture number 10 of this lecture series of VLSI and microelectronics. Now for your easy visibility, it is being given in red color so that you can understand that this course objective is fulfilled after the completion of this course or after the completion of this particular lecture number 10 of the subject VLSI and microelectronics. So let us start. Before starting, let us see the lesson plan of this particular lecture number 10. So our course name is VLSI and microelectronics. The paper or the course code is EC702, and now we are in module 3, that is analog VLSI design circuits. So today we are going to study MOS voltage and current references. Okay, now let us have a quick recap of the previous lectures of in lecture number 8 we have studied about the analog CMOS design, that is we have started the third module. So in the third module, in the starting, we have seen the overview of the CMOS analog design circuits. Why we are studying the analog CMOS designs. Next is MOSFET small signal model. Here in this small signal models, we have studied the basic MOSFET. Next is the channel length modulation model by resistor, and third is the body substrate bias model by current source. And also we have studied the complete small signal model of the MOSFET, considering all the associated capacitances between the four terminals. The next topic we have studied is the MOSFET as a switch. After that we have studied MOS diode or the active resistor. After the active resistor, we have studied the MOS current source and sink. So in the current source and sink, we have seen that NMOS acts as a current sink and the PMOS acts as a current source. And also how and what are the conditions of their acting as current sink and the current source. Next, we have studied the current mirror circuit, why it is called and how it is operating, and also the expressions of the all the expressions like all the G transconductance and all. So let us start today the lecture 10. So the first topic we are going to study is the MOS voltage and current references. The reference voltage or current sources are such sources which are more precise and stable. They must produce stable voltage or current independent of the process parameter, power supply, and the temperature variations. The stability of the reference source with reference to power supply voltage VDD is defined by S of V of reference and V of DDD is equal to delta of V reference by of V reference by of delta of VDD by of VDD. So it is equal to VDD by V reference into delta of V reference by V of delta of VDD. Now, if 10% change in the VDD causes 10% change in the R reference, the sensitivity will be 1. This is a very important line, that if 10% change in VDD causes 10% change in V reference, the sensitivity S will be 1. This is the sensitivity, and this will be 1 if the change in VDD is also 10% and also V reference change is also 10%. So let us go to the next slide. I hope this slide is clear to all of you. Now, this one is the voltage divider diagrams. For first one is the two transistors, next is the two resistors, second one is a resistor and a NMOS transistor, and third one is a PMOS and a NMOS transistor. So there are three cases. So we will go on considering the first case. The first case. The reference sources are required in current mirror circuits, op-amps, comparators, analog to digital converters, etc. These are the uses of the reference sources. The simplest voltage reference circuit can be a voltage divider implemented using either active or passive circuit elements. Okay. So basically, these three were the three different implementations of the voltage divider circuit. So we will go with the first one, that is the resistor based circuit. Okay, this one is a resistor based circuit. Okay, so in the resistor based circuit, the reference voltage can be written as V of reference is equal to R2 by R1 plus R2 into VDD. You can see there are two resistances. This one is the VDD and this one is the V reference. Okay, so in the resistor based circuit, the reference voltage is written as V reference is equal to R2 by R1 plus R2 into VDD. Now this equation shows that the reference voltage is directly proportional to the power supply voltage, and any change in the power supply will cause the reference voltage to change, which is not acceptable for reference voltage source. Hence this simple voltage divider does not work as a reference voltage source. So this is also very important, that this simple voltage divider cannot work as a reference voltage source. Why? Because any change in the power supply will cause the reference voltage to change, which is not acceptable for the reference voltage source. So this one is an important point. So let us go to the next slide. Next is the second case. Okay, now this figure shows an alternative implementation of the voltage reference circuit, replacing the bottom resistance by a MOS diode. Now the previous circuit had two resistors. Now this resistor is being replaced by a MOS diode. This one M1 is the MOS diode. Okay, for the resistor and the MOSFET based voltage divider, we can write that ID is equal to VDD minus of V reference by of R. It is equal to beta of N by 2 into R reference minus of V Tn whole square. So from here what we can write, V reference is equal to V of Tn plus of root over of 2 of ID by of beta n is equal to Vtn plus of root over of 2 into VDD minus of V reference by of R into beta of n. So from here what we can write, R reference minus of Vtn, this Vtn is coming this side, that is V reference minus of Vtn is equal to root over of 2 of VDD minus of V reference by of R of beta of n. Now taking square of both sides of this equation, we can get that V reference minus of, this is a square minus of b, a minus of b whole square. Okay, so this is a square minus 2ab plus of b square, like this formula we written here. A is V reference and b is V of Tn. So it will be V reference square minus of 2 of V reference into V of Tn plus V square Tn. Okay, it is equal to 2 of VDD divided by R into beta of n minus of 2 of V reference by R into beta of n. So we have got this. Now what we can do, we will rearrange this particular expression. Now rearranging the above expression, we are getting R V square reference plus V reference into 2 by R into beta of n minus of 2 of V of T of n plus of, in brackets, V of Tn square minus of 2 of V of dd by of R of beta of n bracket closed is equal to 0. Hence, we can find the reference voltage by writing the root of the quadratic equation of V reference as V reference, that is, this one is a quadratic equation. So we can find the root of the quadratic equation. So we are just applying this formula, that is V of, that is a formula of the quadratic equation we are applying to find the root. So the root is, or you can write the, we can find the reference voltage by writing the root of the quadratic equation of V reference. So V reference is equal to minus of, in brackets, 1 by R of beta of n minus of V of Tn bracket closed plus root over of, in brackets, 1 by R of beta of n minus of V of Tn whole square minus of V of T of n whole square minus of 2 of VDD divided by R of beta n bracket closed. So from here what we can write, V of reference is equal to V of Tn minus of 1 by R of beta of n plus of root over of 2 of VDD minus of V of T of n by of R of beta n plus of 1 by R square beta square n. Okay, that is R square beta n square also you can say. So again what we will do, we will differentiate both sides of the equation. Now differentiating both sides of the equation with reference to VDD, what we get delta of V reference by delta of VDD is equal to half into root over of 2 of VDD minus of V reference by of R of beta of n to the power of minus of half into 2 by R of beta n into 1 minus delta of V reference by of delta of VDD. From here what we can write, delta of V reference by delta of VDD is equal to 1 by V reference minus of VTN into 1 by R of beta of n into 1 minus delta of V reference divided by delta of VDD, that is 1 minus V reference by delta of VDD, or you can write delta of V reference by of delta of VDD is equal to 1 by 1 plus of R of beta n into V reference minus of VTN. So this is the ultimate equation from the above equations. I know that it is a little tedious, but this is a very simple equation, and if you do it one time, it will be very easy for you to do it second time. You have to just practice. So let us move to the next slide. From here, next slide, we will find the sensitivity, as our main objective is to find the sensitivity. Okay. Now, sensitivity we can write as VDD by a V reference into delta of V reference by a VDD. That is delta of V reference by delta of VDD. So from here what we can write, already this value we have find out in the previous slide. So we are writing this value, that is, let us see the previous slide, that is this value we are writing here in this value. So that is, in brackets, 1 by 1 plus R of beta V reference minus of VTN bracket closed into VDD by V reference. Now for VDD is equal to 5 volt, W by L is equal to 2, and K dash is equal to 110 is equal to 110 is equal to, it is not equal to, it will be 110 microampere per volt square, and R is equal to 100 kilo ohm. So V reference will be equal to 1.281 volt and the sensitivity will be equal to 0.283. We are putting these values here. Okay. Now the value of the reference voltage can be increased in the circuit configuration. This is the circuit configuration, that is the where the value of the reference voltage can be increased, and we can write it like this, that V reference is equal to VR1 plus of VR2 is equal to VGS plus of VGS by R1 into R2 is equal to VGS 1 plus R2 by R1. So this one is the circuit where the reference voltage in the circuit can be increased. In this configuration, V reference is given as VR1 plus of VR2 is equal to VGS plus of VGS by R1 into R2, that is equal to VGS into 1 plus R2 by R1. So this MOS voltage and current reference is complete. So from here what we have seen that the reference voltage of the current source are such sources which are more precise and stable. They must produce stable voltage or current independent of the process parameter, power supply and the temperature variations. Now the reference sources are required in current mirror circuits, op-amps, comparators, analog to digital converters, etc. The simplest voltage reference circuit can be voltage divider implemented using either active or the passive circuit elements. These were the uses of the reference sources. So thank you all of you for listening to me and also to the class, and hope we will meet soon, and thank you again.